welcome to another video. Today we're going to be talking about functions of two variables. Again, we'll be talking about a lot of different things over the course of about an hour. We'll do some practice problems, and then that'll be mostly it for this video. And sorry, at the time of recording this video, I am a little bit sick, so you might hear some sniffles and whatnot. So hopefully we can just move past that. So anyway, let's start by talking about multivariable functions. And again, a lot of times what I like to do is talk about functions of like one variable or simplify things before we talk about this more general case. And so what I want to talk about first is going to be functions that look like y equals f of x. And so, what I mean by that is functions of one variable. So you may or may not have seen or heard of what's called a signature of a function, but basically a signature basically tells you what your inputs look like and what your outputs look like. So for a function like this, you have one input x, which is a real number. So we write this boldface r, which is just denotes the set of all real numbers, and we draw an arrow into another r, so which is another real number. So what this means is that what you have here is your input is a real number, x in this case, and then your output is also going to be some real number, in this case y. And so we can use different variable names, but this x and y is going to be a good way for us to capture kind of what's going on. And in particular, we're going to be looking at functions of two variables today. And so here what we have is, well, instead of having one input x, what I'm going to have is a function of two variables, x and y. And my output is, well, this is going to be the next letter in the alphabet, the last one we have, z. And so essentially what we have here is a signature, and it's going to look a little bit different, hopefully. What we have is two inputs, so what we write is R2, and we pronounce that R2. So we have two real inputs, and we combine them in some way to get our output Z, so just one real number. And so some examples of each, maybe for a function of one variable, could be something like this. If we look at the function, f of x equals to sine of x, then what we have here is something that we're used to. We have an input line x and an output line of y. And so we say that our input space is just the set of real numbers. It's just this x-axis. And so we put in one value x, and we get out another value y. So if I plug in x equals 0, I'll get y equals 0. If I plug in x equals pi over 2, I'll get to 1. And then you can fill in the rest of it. You should hopefully know what the graph of sine looks like. Something like this, and so on and so forth. So an example for a function of two variables, what this might look like is going to be, let's take for example the function z equals to, and of course we can write this as a function of x and y. You don't always have to put in this part right here. This can be left out, just like how you can write, for this case right here on the left hand side, you can write f of x equals sine of x, or y equals sine of x. So here, just to note, this part can be omitted. But let's take it as an example, x squared plus y squared. And so again, my inputs are x and y. I combine them in some way. In this example, the combination happens to be I square x and I square y. And then when I add them together, that just happens to be z. And what I'm going to get is something a little bit different. So when we graph this, it's going to have to look different than just two lines. Because now my input, we say our input space is R2. And so my points that I'm plugging into this function can be taken from an entire plane, x, y. And what we have is this part z right here. The z-axis is going to be mutually perpendicular to both x and y. So it's sitting at a right angle to both the x-axis and the y-axis. And so what we have is, in this example, something called a paraboloid. if you've seen that, it's a pretty classic example of a multivariable function. We'll be looking at some other ones here and things you can do with them. This is just to set the stage of what we'll be looking at today. And again, you can have as many inputs as you want. You can have like x1, x2, x3. You can have 10 inputs, 100 inputs. But just for the purpose of Math 2419, we're just going to be looking at functions of two variables when we look at multivariable functions. Okay, so to continue on, something of interest to us is the domain that we have. And so let's go ahead and take a look at what I mean by this. So domains of, how should we call it, multivariable functions. So domains of multivariable functions. So what we're going to have here is, well, let's just go ahead and take an example real quick, and then we'll see what we mean. So let's say I have a function that is, I don't know why this part's up here, I'm good. Okay. Let's take as an example the function z equals to negative x squared minus y squared plus 4. Okay, so there are going to be some points in the xy plane that I can plug into this function and get a defined output, and there are some that I can't, right? And so it's our goal to figure out where this function is defined. That is, define the domain of this function z. And so what we're going to do is, well, note what we have noted before in math. In particular, there are a couple of rules that we can't break. Like we can't divide by 0, right? We can't take the square root of a negative number, things like that. And so in this case, what we're going to get is that, so we say it must be that negative x squared minus y squared plus 4, this has to be at least 0. It can be 0, but it can't be anything less than 0. Right? And so what we get from here, rearranging this, we can add x squared and y squared to the other side. So 4 is greater than or equal to x squared plus y squared. Now I like to have the variables on the left-hand side. And so what we'll do is we'll say that this is the same as x squared plus y squared is less than or equal to 4. Right? And we hopefully know what this looks like. X squared plus y squared is less than or equal to 4. Well, we're going to be somewhere in the xy plane. If we look at x squared plus y squared is equal to 4, what we get is a circle centered at the origin of radius 2. But since we have this less than or equal to inequality, it's going to be everything also inside of the circle. So we're going to get this nice disk. And so what I'm saying is that this area that I have shaded here is going to be the domain of the above function z. So any point xy that satisfies x squared plus y squared less than or equal to 4 is going to be in the domain of this function. So let's go ahead and take a look at some more examples. I'll give you some to work on real quick if you want to get some practice, and then we'll move on. Alrighty, so we're going to do some practice. What we're going to get, well, sorry, not what we're going to get. Let's go ahead and start with the question first, sorry. So we're going to find the domains of the following functions. So we'll have in part A, we're going to do f of x, comma y is equal to square root of x plus the square root of y. B is going to be fxy equals to square root of x plus y. And then in part C, we're going to find the domain of the function fxy equal to natural log of 9 minus x squared minus 9y squared. So if you want to pause the video for just a moment, try to figure these out on your own, and then when you unpause it, I'll go ahead and write the solutions. Okay, welcome back. So what we get in the first part, our solution is going to be, well, we know that, again, our rule is we can't take the square root of a negative number, right? So whatever x value we plug in, it has to be the case that it's greater than or equal to 0. And the same thing for y. And so oftentimes you'll be asked to draw the domain, in which case, for this example, we get x and y are greater than or equal to 0. So we kind of get this quarter plane right here. So hopefully that makes sense to you. Second part looks very similar to the first part. It's a little bit different though. So what we get is we're going to get that x plus y is greater than or equal to 0. If you wanted to think about this another way, we have that y is greater than or equal to negative x. So anytime I have something like greater than or equal to, I just think of it as first as an equal sign, just so we can go ahead and draw whatever function we have, and then we'll look at kind of the region that follows afterwards. So what I mean by that, instead of looking at y is greater than or equal to negative x, we're going to go ahead and look at the graph of y equals negative x. That is, we get this line right here. Again, this is y equals to negative x. And since my inequality is greater than or equal to, so it's all points that are going to lie above this line. So you get this sort of half plane here, all of which are points that I could plug into my function in part B. Let's see, still trying to figure out how to pinch and zoom in this, so if you've been watching these videos, thank you for your patience. Okay, so let's go ahead and look at the last one. I'm going to scroll down a little bit, so we already have the question in our mind. Again, we're going to try to find the domain of natural log of 9 minus x squared minus 9y squared. And again, we arrive at sort of another rule in math that we can't break, I suppose. And that's going to be that we can't take the natural log of a negative number or 0. So basically, a better way to say that is you have to take the natural log of a positive number. And so with that knowledge, right, we can take that and write it in some sort of algebraic inequality. That's what we're going to get for this example in part C. Our solution is going to start by looking at the fact that 9 minus x squared minus 9y squared has to be greater than 0. So this is going to be strictly greater than, not greater than or equal to. And so again, this is where you start, and then from here we're trying to get some equation of some region that we know and can sketch in two-dimensional space in the xy plane. And so from here, I like all my x's and y's to be positive. And so what I'm going to do is add them to the other side. So I get 9 is greater than x squared, and then I'm going to add to it 9y squared. Again, I like to have my x's and y's on the other side. So I do x squared plus 9y squared is less than 9. And then what I'm going to do is divide everything through by 9. So I get x squared over 9 plus y squared is less than 1. Okay, and so hopefully you remember what this looks like. This is going to be the graph of an ellipse. And if you wanted to write it, you could do x over 3 squared plus y over 1 squared less than 1 to see that the graph that we get is going to be an ellipse. It's going to be a, how do I want to say, like a horizontal ellipse, I suppose. And so I'm going to go out 3 units in the x direction. and then I'm going to go up and down just 1. And again, I get these numbers by looking at the fact that I divide x by 3 and y by 1. So what I get is something like this. Looks kind of like a football or an almond. But basically, I kind of did something wrong. Here we have something to note. This is strictly less than 1. And so I should have done this dotted line here to indicate that the boundary is not included in the domain. So it has everything inside, but not along the boundary. So hopefully that makes sense. Again, just to kind of scroll up just to see again, we just basically talked about functions of 2 variables, kind of what they are. And now we look at domains in this in practice. So again, it's nothing too crazy. Just now that our domain is not just like the x-axis, not a line, but rather a plane. Okay, so we're going to jump into our next topic for today, which is going to be level curves. Again, this is something that's related to multivariable functions. And typically, this is your first time seeing it. For those of you who've taken calculus in high school, you probably would not have seen this before. And so we're going to look at, let me get this right before I start going crazy here, level curves. Okay, so again, we would say R3. So we have an x, a y, and a z axis. So things get a little bit more tricky, but I find more fun to draw in. And so what we're going to do first to introduce level curves is going to just say that we have some function, right? So imagine we have a function. Let's give it a color. Let's say we have a function, no, not that color, bad color. Z equals to f of x, y. And so what we're going to do with this function is set it equal to different constant values. So basically what we say is we obtain level curves by setting z equals to k, where k is just some real number. So k, you would read this, k belongs to R. Okay, so let's pause and think for a moment what exactly this means. And a good way of doing so would be looking at a case of, again, one variable. And so what I want to do, just for the moment, is look at something like this. And I'm going to erase this here in a second, just so we have more room. But what we're doing for level curves is we're setting z equal to some number, z equal to 5, z equal to 7, whatever number we choose. So let's think about what happens when we do that in the case of 2 variables. So what we have for level curves is setting z equal to a number, and again, z is our output variable. If we're in 2 dimensions, our output variable is going to be y, in which case if we set y equal to some number, like for example y equals 3, well, we know that that's just going to be some horizontal line. Right? This is going to be y equals 3. And as I increase the value I set y equal to, like y equals to 5, this is going to shift up. And if I decrease it, this bar is just going to shift down a little bit. And so what we get is some line, right? What we're going to get for level curves when we set z equal to something is not going to be a line, but a plane. So I guess I'll keep this here. I guess I lied. So what we're going to look at, just get a new color. So we have, of course, always x, y, and z. And so let's say I have the function f of xy equals to x squared plus y squared, like we had earlier, the square root. And so what this turns out to be, not to kind of spoil it if you don't know, but what we get is a cone. It's a nice ice cream cone. And so what we want to look at is setting z equal to different values, right? So we're going to look, for example, at, let me think right here, z equals to k. So we'll have this table. Let's do 1, 2, and then 4. Excuse me. And so if we set z equal to 1, right? Well, z is just square root of x squared plus y squared. So that's equal to 1. And that means, I guess I can get rid of this. This doesn't really help us out too much. We get that x squared plus y squared equals 1. And so in each case, I'm setting z equal to this. Hopefully this makes sense. X squared plus y squared is 4. So here is z. Here's my different values of k. Right, so I'm setting them equal to each other. What I'm getting are these functions, right? And so when I get the equations, I should say, the second one's going to be x squared plus y squared equals 4. And the last one's going to be x squared plus y squared equals 16. So let's go ahead and pause for a second. I know this is a lot to look at. Let's just look at this first row right here. Now when I set z equal to 1. So setting z equals to 1 means I go up 1 unit in the z direction. And I'm going to look at the equation z equals to 1. Right? So z equals to 1 is going to be a plane with a height of 1. Basically think of this as the xy plane. It's moved up. Every point's moved up 1 unit. And so this right here is this. Setting the k equal to 1, k equal to 2, whatever. And then what I get is I'm going to take the intersection of this red plane and my cone, the function that I have of interest. What I'm going to get is this circle right here, right? And this circle is going to be the exact circle x squared plus y squared equals 1, right? Now let's increase z a little bit. So let's increase this. What I'm going to get is a plane that's way up here, and where this intersects the cone, I'm going to get a bigger circle. Do it again, I'm going to get a bigger circle. And so basically, what we see is as z increases, the radius of our circle increases. And this is, of course, the circle where the plane intersects the cone. The radius of the circle increases, which should make sense with what we have right here. Look what happens as k increases, or z, and then look what happens on the right. Right, these circles are getting bigger and bigger. So this is essentially what a level curve is. So hopefully that made sense. A lot of things get kind of more confusing. Maybe I shouldn't say that. They get harder to visualize when you look in R3. But if you put in the work to kind of visualize it or just watch different animations online, I think you can really understand it and get a good intuitive understanding of what's going on. What we can also do, another way of writing this information that we had, is let's look at the xy plane. And I'll make this just a quick sketch before we do some examples. So what I had when k equals to 1, right here again, this first row, is I had the circle x squared plus y squared is equal to 1. Right, so let's go ahead and draw that circle. So this is x squared plus y squared equals 1, which I obtained, of course, when k equals 1. So I got this when k equals 1. If we do k equals to 2, I get the circle of radius 2. And then if I do k equals 4, I'm all the way out here. So this is where some interesting intuition can kind of come in. So each of these circles we obtain by taking this intersection, these circles that I got right here. Let me get a color. These circles I got right here, and flattening them down to the xy plane. Right. So essentially, k equals to 1 means that this circle right here has a height of z equals 1. The second circle has a height of z equals 2, and so on and so forth. So this is just another way to kind of visually see what's going on when we have level curves of the function. Okay, so hopefully that makes sense. Let's see if I have any practice questions. So I suppose what we could do just as something to work on, a practice problem, and I'm not going to walk through this one necessarily. Practice. Take the function z equals to, let's see what I could do here, square root of x squared plus y squared plus 10, I believe. I don't know if this is going to work. Let me see. Sorry, give me 1 second. Okay, so what we're going to do for practice is we're going to take the function z equals to x squared plus y squared minus 16. And so take this function and find its level curves for the values. So I'll give you values here to work with. Z equals 0. Let's do z equals to, I'm trying to think of some good numbers here. Z equals to 7 should be fine. Let's see, 12 and then 16. So you're going to take these values, set this equation right here. So instead of z, just write these different numbers and see what equation you get. And then see if you can kind of use the composition of those images or those level curves to figure out what this graph looks like in 3D. And if you can't figure it out, there's some good online resources for 3D graphers. You can go ahead and try that out. But hopefully what I just said makes some sense. So I will, again, leave that question here. Alright, so let's go ahead and move on to our next topic. So our next topic is going to be partial derivatives. So again, now that we kind of know what functions of multiple variables are, we have to define them. It's important for us to be able to do calculus with them. So we're going to take derivatives. And so what we had, and this is going to be probably the most important part of the video, in elementary calculus, we had some function in the xy plane. So we had x and y, and then some function f of x. And what we did was, let's say that there's some point right here that has an x value of x naught. What we were often interested in was taking the derivative of whatever function I have, evaluating it at x naught. Right? And that tells me the slope of the tangent line to the curve at this point. Now, what we're going to be doing with multivariable functions is going to be a little bit different. So I'll draw it over here, just in this thicker color, because I have room. So what I have is x, y, and z. And so what I'm going to have here is a function maybe that looks like this. And what I'm going to have is, so this function is going to be f of x comma y. And so when we have something like this, I can't necessarily just say, what's the derivative of this function, right? because we have two variables, and actually because of that we have to specify which variable we're taking the derivative with respect to. And so what we have is, so we denote f sub x to be the partial derivative of f with respect to this variable x. So this letter here, sometimes pronounced daba, it just specifies our partial derivative. We do that because we have a function of more than just one variable. Fy function, the derivative of our function with respect to y is going to be partial f partial y. And so a good way of thinking about this is that when you take the partial derivative of a function with respect to a variable, you hold all the other variables constant. So in this case, we only have one other variable. So when we take the derivative of f with respect to x, y is held constant. Here, x will be held constant. And so again, that should mean something to us, visually, geometrically, right? And so what we have, when y is held constant, what we have is the plane y equals whatever number. Like, for example, we can look at y equals 1. We're going to take a look at this plane that we get. So up, something like that. And this plane is going to intersect the function that I have. What we're going to get is some little curved path here, wherever the intersection takes place. And then what you should note is that, well, let's imagine that we're an ant walking along this red dotted path. So when I'm doing so, my z value is not going to change, right? Because points are going to be of the form x, y, and z. And so along this path that I just drew, y is not changing because, by design, y is constant, right? So what's going to happen is all I have is changing is x's and z's, right? And so what I can ask is, well, as x changes, how does y respond? Sorry, as x changes, how does z respond, right? And that's exactly our original formulation of derivative that we have on the left-hand side. As my input variable tweaks a little bit, how does my output variable respond? And so the way we think about that is, let's say that I'm at this point right here, and we want to go in the increasing direction of x, which is this direction here. So this is the increasing direction. That is, if I walk along that direction, x will increase in value. And so as we go that way, we want to look at the slope right here, this line. And so the slope right here is going to be partial derivative of my function f with respect to, well, of course, x. The picture's getting a little bit cluttered, but I just got to finish it out just for the sake of, doing everything. And so what we get also, if we hold x constant, and maybe x equals 2. And again, this choice of 1 and 2 for these values of x or y and x are arbitrary. It could be any value. I just wanted to pick something just so we could see things easily. So what I get here is another path where this plane x equals 2 intersects this function. And I apologize if this is getting so cluttered. But at this point here, they go in the increasing direction of y. It looks like z is going to decrease, so here we would just have partial derivative of f with respect to y. So this is a good picture. I'm actually kind of proud of it. So hopefully you can kind of sketch it out yourself, make sure that things make sense. And now that we know visually what's going on, we can kind of do some algebra. And so let's go ahead and look at a couple more things, and then we'll do an example, I promise. Okay. Excuse me. Okay. So some more notation. So we can also have higher order partial derivatives. So, when we have like a derivative, we can take a second derivative. It tells us like the concavity of our function. What we can do is we can take, whoops, don't want that color, nor thickness. We can look at f sub x, which means we take the partial derivative with respect to x of the partial derivative of f with respect to x. So this is called a higher order partial derivative. This would particularly be a second order. And what we can do is write this as partial squared of f over partial x squared. Similarly, with the second derivative with respect to y, f by y, we get this. I'll kind of go through this a little bit quicker. Alrighty. But we also have something, and I suppose I should explain these real quick. So if fxx or fyy is positive, our graph would be concave up at that point. So exactly the same as we had in elementary calculus. And of course, if either of them at a point is negative, it's going to be concave down. But this is going to be concave up and concave down in different directions. So what we could get is something like a saddle point, which we'll talk about more in the future. Before we move on, let's talk about a special case, fxy and fyx. So here what we have is, first we have the function f, its derivative with respect to x, and then we take the derivative of that function with respect to y. And so what we have is we get partial derivative with respect to y, this operator outside, because we're taking the partial derivative with respect to y of this right here. And so we write that as partial squared of f over partial y partial x. And so what you'll notice is that we kind of have some contradictory notation. So if you look on the left, we have fxy. So the order in which we take the derivatives goes from left to right. Sorry. So first, we take a derivative with respect to x, and then a derivative with respect to y. But what we have here is the opposite. So here, the first one we do is on the right. So first we take a partial derivative with respect to x, and then derivative with respect to y. And so in this case, what we have here, partial derivative of y with respect to x. And again, I'll kind of do this one a little bit quickly. Again, to obtain, now what we're going to have is the flip, so partial x, partial y. And under suitable conditions, these two right here, fxy and fyx, will actually be equal. So this will be something that you'll see a little bit more later. But let's go ahead and do a quick example, just so we can actually say we had some practice. And then we will move on from there. Okay, let's see. So our question is going to be, so let's get a nice thick marker. So find, we're going to find fxx, fyy, fxy, and fyx for the function z equals to x times sine of y minus y squared x cubed. Okay, so maybe not that. Okay, so let's go ahead and take a look at this one. So to find these ones, we first must find partial derivative with respect to x, partial derivative with respect to y. So for the partial derivative with respect to x, we go ahead and look at the function, and we see that z equals x times sine of y minus y squared x cubed. And so the multiplier of the x is sine cubed, so we get sine of y. This again is y is constant with respect to x. And then what we get is minus 3y squared x squared. So if that didn't make sense to you, think of y as just some number, right? It's just constant. And so if I have any expression of y multiplying, for example, an x, like right here, then all I'm going to do is write this function is like linear in x. And so I'm just going to pull out the constant coefficient in this case, which would be sine of y. So for the partial derivative of x with respect to y, we look at x times sine of y. So x is just multiplying it, so x is just going to stay there, it's going to hang out. And then the derivative of sine of y, well, since we're taking the derivative with respect to y, we would just get cosine of y. And then here, we get x cubed, it's copied down. And the derivative of y squared would be 2y. Okay, so now from here we can find our higher order partial derivatives. And so what we get is f, so we want to find fxx. So what we get is now we take this function right here and take its derivative with respect to x, which means we would simply get negative 6y squared x. For fxy, we take the function we just had, take its derivative with respect to now y, we get cosine of y minus 6yx squared. So we're good on this one, fxx and fxy. So now we're going to take the partial derivatives, we're going to take the remaining partial derivatives, looking at this function first. So f, y, y, excuse me. Okay, sorry, I'm back. Fyy is going to be negative x sine of y minus 2x cubed, and fyx is going to be equal to cosine of y minus, what do we get here? Fyx is going to be minus 6x squared y. So there's something that you should be able to notice between fxy and fyx, and that is that they are equal. I wrote it a little bit differently, but again, we talked about this not too long ago, that under suitable assumptions, that these partial derivatives are going to be equal. Okay, so I'll give you another one just to kind of work on your own, and then I'll kind of give the answer. I'm just trying that out more, I suppose, in this video. So what we're going to do is one last question before we move on to our final topic for the day. So what you're going to do is find, so we're going to have a function f. We're going to take this crazy sequence of partial derivatives, x, x, y, z, z, for w equal to z cubed, y squared, natural log of x. So again, I'll kind of leave you this one to work on. So you can pause it real quick, because I'm going to write the answer here in a second. Okay, now assuming you're back, the answer to this question is negative 12 zy over x squared. So hopefully that went well with you, and I hope that the answer I just gave was not wrong. But this is what we're going to have for this question. Okay, so what we're going to talk about now, for the rest of the video, are going to be different types of derivatives. And so first, what we're going to have is the case of like explicit differentiation. Excuse me. Okay, so for this sort of, I guess, case or type of differentiation, I should say, that we're looking at, we're going to have two different cases. So case one is going to be that of the total differential. So case one is going to be total differential, which we can use in some interesting applications. Case 2 is going to be our partial derivative. It's a little bigger. Case 2 will be that of our partial derivatives. And so we see these two side by side, so they're kind of different in some sense. On the left we have a total derivative, total differential. On the right we have partial, so total versus partial. So we're going to do, excuse me, is now we're going to look at the case where we have z as a function of x and y, where x is some function of another variable and y is a function of another variable. Let's go ahead and pause and see what this means for a second. So z is a function of x and y. Those are the things that input. But x and y in turn are functions of another variable t. And so what we have is this nice little graph, or this little visual, I suppose, that helps us kind of get this information in our head. So what we have is z is a function, two variables, x, y, which are in turn functions of t. So the branches tell you what variables are, sorry, which, what is a function of what variable, I should say. And so in this case, we're interested in the total differential, which is dz dt. And so z has to go down this path of branches to communicate, to get to the t. So what we get is, this is the partial derivative of z with respect to t, with respect to x. Again, because z is a function of more than one variable. But then what I get is just times dx dt. Again, here just a single variable case. Plus partial derivative of z with respect to y now, going along the second branch, times dy dt. Okay. On the right hand side, what we're going to have is something a little bit different, not too entirely different. So we're going to have z is a function of x and y. X is some function now of two variables. Instead of t, it's going to be s and t. And same thing for y. So some other, potentially different function of the same variables. So for here, our drawing is going to look like this. You get x and y. So now we have two more branches. S, t, s, t. And so for example, if I wanted to, let's see, if I were so inclined to take the partial derivative of z with respect to s, now what I have to do is go down every branch pathway that gets me to an s. And what I do is each time I cross like an edge, I'm going to write that respective partial derivative. So here I go from z to x. So sorry, partial derivative of z with respect to x times partial derivative of x with respect to s. Sorry, s plus partial derivative of z. Now I'm going down this part on the right. And so z talks to y, and then y talks to s. So this is essentially what I have for partial derivative of z with respect to s. Of course, we could take partial derivative of z with respect to t, and it would not be too entirely different. Okay, so hopefully this makes sense. So go ahead and kind of get this copy down, or just make sure this makes sense to you before we look at this next example we have. Okay, example. So what we're going to do is compute dz dt, the total differential, because we have d's, not the other sort of letter gamma, for z equals to x times e to the xy Now x and y are in turn going to be functions of another variable, in this case t. So we'll say that x is equal to t squared, and y is equal to t to the minus 1. And so we're going to do this two different ways. First way, we're going to do it by the formula we have above, which is technically the chain rule. And then we're going to do it a second way here in a second. So let's do it this first way. And so what we have, again, the formula is going to be dz dt is partial derivative of z with respect to x times dx dt plus partial derivative of partial derivative of z with respect to y times dy dt. And we'll pause here for a second just to note that we're taking the derivative of z with respect to t. So our final answer should be in terms of t. So this is just something to keep track of, right? So let's go ahead and do all of our side work here. And then we'll plug it into the formula we have. So we need to find the partial derivative of z with respect to both x and y. So we'll do that first. So partial derivative of z with respect to x. So we have a product of two functions of x, so to use the product rule, we're going to get x times e to the xy, so we're going to take the derivative of that with respect to x, plus e to the xy times the derivative of x, so just e to the xy. And so we get e to the xy, factor out of both, we're just left with x squared plus 1. Partial derivative of z with respect to y is going to be simply, I think I did this wrong. Yep. Okay. I made a mistake on this previous one. This right here should be a y. Sorry. xy plus 1. Right, because it's taking a derivative with respect to x. So the y would be the coefficient and the exponent, so that's what comes down. Okay, so in here, what we get is simply x squared times e to the xy. Okay, we need two more things, dx dt and dy dt. Dx dt is simply going to be 2t. Dy dt is going to be negative t to the negative 2 power. So now plugging all of this into here, what we get is dz dt. So you get partial derivative of z with respect to x. So we get e to the xy times xy plus 1 times dx dt, which is 2t, plus now x squared e to the xy times negative t to the negative 2. Alright, so we'll pause here for a second just to note that we have x's and y's right here, and we also have t's, which is not necessarily what we want for a final answer. So what we're going to do is plug in for x and y their corresponding functions of t, right? So instead of having e to the xy, I'm going to have e to the t squared times t to the minus 1. And then I'm going to get that again here, t squared times t to the minus 1. So I'll scroll down a little bit just to give ourselves room. Plus 1 times 2t. Plus, now here I have this problem, x squared e to the xy. So x is again t squared. So t squared squared e to the t squared times t to the minus 1 times negative t to the minus 2. So I'm going to bring this negative outside here. I'm going to get t to the minus 2. So what I get overall is e to the t times t plus 1 times 2t minus t to the fourth, but I also have a t to the negative 2 out here, so I have t squared e to the t, which gives me e to the t factored out from both of them. And then what I'm going to get is 2t times t plus 1 from the first minus t squared. And again, I hope this is right. So this is what we got. This is the total differential for dz dt. It's going to be e to the t times, in parentheses, 2t times, again in parentheses, t plus 1 minus t squared. Okay, so now we're going to do the same question again, but in a much easier way. And the way that we're going to do that, so let's see, did I have part 1? Yeah. So in part 2, we're going to solve this same thing by first converting z into a function of t before differentiating. So what do I mean by that? Well, we had the z was x times e to the xy. Again, so we'll recall x was equal to t squared, y was equal to t to the minus 1. So I'm going to plug in those expressions in for x and y to get t squared e to the t. And now simply take the derivative with respect to t. So you can see how this is hopefully a lot easier than what we just did. We'll have to do the product rule here. So we're going to get t squared times e to the t plus 2t e to the t. So what I get is e to the t times t squared plus 2t, which there's a t in there, t e to the t times t plus 2, which should be the same as what we got. 2t squared plus t. Let's see. So if you look at what we had here, right, I can multiply this through to get e to the t 2t squared. Then I have a minus t squared right there, plus 2t. Probably should have done this at first. So what we're going to get is e to the t squared plus 2t. Subtract out to t, we get t e to the t plus 2. So hallelujah, they're the same. Okay, good. So again, here's all our work for part 1. Scratch work, and algebra included. And then part 2, simple 2-liner. So much easier way of doing things. So hopefully that made sense. So also in your class you have the partial derivatives and total derivatives for implicit differentiations. So I'm going to give you those formulas just because I want to walk through some example for the total differential, like the application. And then we'll go ahead and call it a day. So again, what we had first was, scrolling back up, explicit differentiation. Now we're going to look at its counterpart, implicit differentiation. Implicit differentiation. And in this case, I'm going to walk through it very quickly. So in the first case, we're going to look at total derivatives. Sorry. Again, I'm still a little sick. Okay. Total derivatives. So what we're going to do is first suppose we have some function, capital F of xy is equal to 0. If I take the derivative with respect to x of both sides, then what I get is by chain rule, partial derivative of f with respect to x times dx. because x and y here are not assumed to be functions of other variables. Actually, that might not be true. Let's go ahead and finish this first. Partial derivative of f with respect to y times dy dx equals 0. This, of course, is going to be equal to 1, so we're not going to write it. And instead of writing partial derivative of f with respect to x in this way, I'm going to write capital F subscript x plus f sub y dy dx equals 0, which implies that dy dx is going to be negative f sub x over f sub y. So sometimes you'll have to use this. I just wanted to write it down just so we can have done it. And then for partial derivatives, we'll go ahead and look at those real quick. Again, sorry, it's going to be a little bit fast. Just had to work through something a little bit quickly just to get to my final point. Not have this video be too long. So the second one for implicit differentiation is going to be partial derivatives. So in this case, I suppose type, what we want to find are partial derivatives, right? So we're setting out to find partial derivative of z with respect to x and y, which of course are going to be our inputs, given that we have some function capital F x, y, and z equals 0. And so here we work with this equation on the right hand side again in the same way we did last time. Now let's say we wanted to find this one first, partial derivative with respect to x. So what we do, we take partial derivative with respect to x, this, and that's going to be equal to partial derivative with respect to x, 0. So what we get is partial derivative of f with respect to x, and then we get partial x times or over partial x plus partial derivative of f with respect to y, partial x, plus partial derivative of f with respect to z, partial z, partial x, all equal to 0. This is going to be 1. Sorry, I should maybe do this in a different color. Oh, nice. Okay. This is going to be 1. And what we do here is say that this is equal to 0. The reason being is that we're treating y as a constant, which is sort of our tacit assumption here, in which case this whole term goes to 0. And so what we're left with at the very end is that f sub x plus f sub z times partial derivative of z with respect to x equals 0. This will imply that the partial derivative of z with respect to x is equal to negative capital F sub x over capital F sub z. And so similarly, we can look at this for partial derivative with respect to with respect to y, in which case we get partial of z with respect to y is negative f sub y over f sub z. Okay, so we're going to look at a quick application of the total differential. Again, this is kind of going back to what we had before, an explicit differentiation, and then we'll be done for the day. Yeah. Okay. So what we're going to get is, for example, this question. Use the total differential to approximate this value, square root of 2.98 squared plus 4.03 squared. So let's say you didn't have your calculator, your phone, laptop, computer, whatever, and you were trying to find the value, this value right here. And so what you would do, well, it's actually kind of a difficult thing to do, right? And so we're going to use the total differential to approximate this value. Again, so we see that 2.98 is some value that's close to 3, and 4.03 is some value that's close to 4. And so what we're going to use is the close by values here to approximate this. So what I mean to say is I'm going to do the following steps. And so what we're going to have first, let's consider a function. So let's consider the function f of xy equals to square root of x squared plus y squared. Again, this is going to closely model what we have here because we have the square root of something squared plus another thing squared. And so part 2, what we're going to do is we're going to look at f evaluated at the point 3, 4, because again 2.98 is very close to 3, 4.03 is very close to 4. And so this is what we're going to call x naught. This is what we're going to call y naught. And so what we get in this case is the nice value of square root of 3 squared plus 4 squared, which is the square root of 25. Should be, of course, 5. Okay? And what are we actually trying to know, right? What we want is f of 2.98 comma 4.03, right? Because f is the function square root of x squared plus y squared. If I plug in 2.98 and 4.03 as my respective x and y values, then I'm going to have exactly what I originally wanted to find out. And so what we do is we say that, just to kind of scroll down a little bit, use a different color. Let's see here. We'll say that f of xy is approximately equal to, f of x naught y naught plus some little change, so this dz that I have. Right? And what this dz will be, if you recall the total differential that we had before, this is just going to be, we had partial z with respect to x, dx dt, plus, let me erase this real quick, sorry. So what we had was that dz dt was equal to partial derivative of z with respect to x, dx dt, plus partial derivative of z with respect to y, dy dt, all times d. So basically what we have is this for now. But what we can do is we can multiply the whole thing through by dt, in which case we'd get dz is going to be f sub x instead of partial derivative of z with respect to x, dx, plus f y dy. This is going to be what we're going to use right here for dz. And so what we get is, this is approximately equal to f x naught y naught plus fx at the point x naught y naught times dx, which is just a change in x, so x minus x naught, plus fy evaluated at the point x naught y naught, our approximation point, times y minus y naught. So hopefully this makes sense. This is a pretty important thing. You'll definitely see this in class. So what we get for this example, so our answer is going to be f of 2.98, 4.03 is approximately equal to 5 plus 3/5 of negative 0.02. So this comes from here. Again, this is going to be the 3 minus the 2.98 plus 4/5 of 0.03. And so I got the 3/5 and the 4/5 by taking the partial derivative of this function right here with respect to x and y, then evaluating them at x0 and y0. And so what we get is about 5.012. Alright, so that concludes this video. Thank you for watching and have a good day.